Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course. States of matter. Today we will begin with lecture 13 from the course, but make sure you watch the previous ones before viewing this one. So we are discussing the gas laws, and we have already discussed three gas laws, that is the Boyle's law, the Charles law and the Gay-Lussac law. And in all these three laws, we have studied that there are four measurable properties of the gases which are interrelated to one another. And we have learned the relationship between these while we were studying those three laws. We saw that the Boyle's law, this gives us the relationship between pressure and volume, both being inversely proportional when the quantity of the gas as well as the temperature is going to be constant. Then we learn the Charles law, which gives us the relationship between volume and temperature, both being directly proportional when pressure and the amount of gas is fixed. And then we learned the Gay-Lussac law, which was the last law that we discussed, where we saw the relationship between pressure and temperature when the amount of the gas and the volume of the gas, this remains constant. But till now, we have not discussed the relationship of the fourth measurable property with any of these: pressure, volume or temperature, that is the amount of the gas. So in today's lecture, we will be discussing the relationship of the amount of the gas with volume, and the law which gives us this relationship is going to be the Avogadro's law. So the Avogadro's law, this gives us the relationship between the volume and the amount of the gas. And I hope you now understand what is going to be constant when the pressure and temperature of the gas is going to be constant. And this law is known as Avogadro's law, behind the name of the scientist who gave the law. He was an Italian scientist, Amedeo Avogadro, and he gave this law in the year 1811. So let us understand this law. So the Avogadro's law, this is based upon the results of two very important things that were known to Avogadro. And those two important things that were known to him was the Dalton's atomic theory and the Gay-Lussac law of combining or gaseous volumes. And the results he got from these two, when he combined them, what he gave a statement to us is known as the Avogadro's law. Now you've already studied what is the Dalton's atomic theory. You've already studied the Gay-Lussac law of combining volume while we were doing the course on some basic concepts when you were learning the laws of chemical combination. And in fact, the Avogadro's law also you learned at that time. But it is important for us to now bring this law back again, because we are studying the gaseous state of matter, and this is going to be very important for us to have a relationship of the amount of the gas with pressure, temperature and volume, so that we have a thorough understanding of all the four measurable properties of the gases. So I will be quickly revising with you what is the Dalton's atomic theory, the Gay-Lussac law of combining volume, the Avogadro's law, what we have studied in some basic concept, but that would be a quick revision. In case you want a complete understanding, if you've forgotten anything, your concepts are not still clear, please go back to the course on some basic concepts. There we have on our channel a complete course on some basic concept, and you can watch each and every lecture and have a thorough understanding. Now, before I do that, well, I would like to just want you to just have a look at what is the Avogadro's law and how we learned that in the course on some basic concept, how we reached up to that point. So what we have for the Avogadro's law statement is that equal volumes of all gases under the same conditions of temperature and pressure, they contain equal number of molecules. Now this means is that as long as the temperature and the pressure remaining constant, the volume of a gas is going to depend upon the number of molecules of the gas or the amount of the gas. More is going to be the number of molecules or the amount of the gas, more is going to be the volume. If it is going to be less, the volume is also going to be less. So what we can say is that V is going to be directly proportional to N, or V is equal to K4 into N, when K4 is going to be the proportionality constant for this fourth law that we have learned. So we have have already learned that K1, K2, K3 were the three proportionality constant for the Boyle's law, the Charles law, and the Gay-Lussac law. So now when we learn the Avogadro's law, K4 is what we are using. So V is going to be equal to K4 into N, and what N is the number of moles of the gas. So already you have learned in the three laws that we are saying that the amount of the gas, we are going to specify the number of moles of the gas. Now why do we do that? Well, we do that because you all know that the size of the molecules is going to be very small. So you cannot keep on counting the number of the molecules that are going to be related to the volume. So in practical life, in everyday life, what we require is something that we can quickly measure. So what that quickly we can measure is the mole. And you already know what is a mole. Well, when we know, I hope I'm not going to revise all this with you. You already know all that. So the number of molecules in 1 mole of a gas, this is going to be equal to 6.022 into 10 power 23, which is equal to the Avogadro's constant. So it was Avogadro, while he was doing all his experiments, that he gave us that 1 mole of anything is going to be equal to 6.022 into 10 power 23 species. Fine. So here also, when we are going to say that it is going to be 1 mole of a gas, the number of molecules in 1 mole is going to be equal to 6.022 into 10 power 23 molecules. Now what we get from V directly proportional to N is that we can say that V by N is equal to K4, or we can say that V1 by V2 is going to be equal to N1 by N2. And I hope I do not have to draw all these graphs also with you. We have been discussing a lot many graphs and you have an understanding of the graph. So what we will be getting as far as a graph, if I have to draw, is going to be that when I take the amount of the gas on the x-axis, the volume on the y-axis, what I am going to get is that V is directly proportional to N. So this is the graph that we will be getting, right? So if there are going to be any other variations, I hope you can now handle, because we have done all this in great detail. Now, the next thing is going to be that I will be quickly recapping the Dalton's atomic theory and the Gay-Lussac law and how we reached up to the Avogadro's law. So the Dalton's atomic theory, this was my lecture number 3 from the course on some basic concept. I've just picked up the slide from there. So when we talk about the Dalton's atomic theory, what is going to be important for us as far as this law is going to be concerned is that Dalton said that matter is made up of very small indivisible particles called as atoms. And well, the limitation of his law when we gave his law was that he could not differentiate between the atoms and the molecules. So what we got as the limitations of Dalton atomic theory, that he could not distinguish between the ultimate particle of an element and a compound. So for an element, the smallest particle that is capable of having an independent existence is an atom, whereas for a compound it is going to be a molecule. What Dalton said was that for both of them, the element, the smallest indivisible particle, is going to be atom, and for compound he said it is going to be compound atom. So he could not differentiate between an atom and a molecule, and whereas what we got a problem relating to the Dalton's atomic theory to the law of gaseous volume. So the Dalton's atomic theory, he failed to explain the law of gaseous volumes. So let us quickly recap what was the law of gaseous volumes. Now, the Gay-Lussac law of gaseous volume states that when the gases they combine or they are produced in a chemical reaction, they do so in a simple ratio by volume, provided all the gases they are at same temperature and pressure, right? So, for example, what we learned was that if chlorine gas is going to combine with hydrogen gas, what we will be getting is HCl gas. Okay, so if we have 1 volume of chlorine gas combining with 1 volume of hydrogen gas, we will be getting 2 volume of HCl gas, and the ratio of the volumes of these 3 gases is going to be 1:1:2, which is a simple whole number ratio. Now the conclusions of this as well as the Dalton's atomic theory, they were combined by a scientist known as Berzelius. So Berzelius, he gave his hypothesis by combining the Gay-Lussac law of gaseous volume and Dalton's atomic theory, and according to him, under the similar conditions of temperature and pressure, equal volumes of all gases, they contain equal number of atoms. And he did an experiment to prove that, and what he found was that when hydrogen and oxygen, they combine to give us water vapors, all three gases, please do remember that it is going to be a relationship of all gases only. Do not just write simply water, because water is going to be a liquid, right? So hydrogen gas combining with oxygen gas to give us water vapors, and what he found was that two volumes of hydrogen, they combine with one volume of oxygen to give us two volumes of water vapors. Now, according to him, under similar conditions of temperature and pressure, equal volumes are going to contain equal number of atoms. So, if supposedly one volume is going to be equal to n number of atoms, the number of atoms in going to be that in hydrogen is going to be 2n atoms. So, 2n atoms of hydrogen combining with n atoms of oxygen to give us 2n atoms of the water vapors. Now, what we can write this also as is that two atoms of hydrogen is going to combine with one atom of oxygen to give us two compound atoms of the water vapors, because this is what Dalton had said. Dalton had not distinguished between atoms and molecules. So from this, if we write further, what we can write this as is that one atom of hydrogen is going to combine with half an atom of oxygen to give us one compound atom of the water vapor. Now here is where the problem comes, because Dalton said that the atom is indivisible. So how can half an atom of oxygen combine with hydrogen? Right? So this is why Dalton could not explain the Gay-Lussac law of gaseous volume. Fine, this is one thing. Now there was a modification done for the Berzelius hypothesis, and that is what we have as the Avogadro's hypothesis, which later on came to be known as the Avogadro's law. So Avogadro, when he modified the Berzelius hypothesis, he was the one who differentiated between the atoms and the molecules now. And he said that under similar conditions of temperature and pressure, equal volumes of all gases, they contain equal number of molecules. So what we had seen for the experiment between hydrogen and oxygen forming water vapors, what we get is that two volume of hydrogen combining with one volume of oxygen to give us two volumes of water vapors. So this means that now not atoms, but it is going to be 2n molecules of hydrogen, which is going to combine with n molecules of oxygen to give us 2n molecules of the water vapors, or two molecules combining with one molecule giving us two molecules of water vapor, or one molecule of hydrogen combining with half a molecule of oxygen and forming one molecule of water vapor. And now, because the molecule can be subdivided, this result was not in conflict with the Dalton's atomic theory. So here the correlation between the Dalton's atomic theory and the Gay-Lussac law of gaseous volumes was achieved, and Avogadro, he gave this very important law to us that under similar conditions of temperature and pressure, equal volumes of all gases, they are going to contain equal number of molecules. Now please remember, it is going to be all gases, whether it is hydrogen gas or it is going to be oxygen gas. Their masses, they are different, but when the volumes, they are going to be same, the number of molecules are going to be same. Okay, so whenever it is going to be two gases whose volumes, they are going to be same, they are going to contain equal number of molecules, or you can say equal number of moles. So now what we have learned in this law is that volume of a gas, this is going to be directly proportional to the number of moles of the gas when the temperature and pressure, they are going to be constant. Fine. So now we are going to learn certain more things related to this law, which are going to be very important for us. So the first thing is that 1 mole of each gas at STP, this has same volume, that is, it is going to be 22.7198 liter, and this is known as the molar volume of the ideal gas or a combination of gas. So whenever we are going to have 1 mole of any gas, or it is going to be 1 mole of a combination of gases also, at STP, I'm just coming up to what is this STP. It is going to have same volume. right? So first of all, let us understand what is this STP. So STP is standard temperature and pressure. What we have said is that we need to have a constant temperature and pressure, and when this temperature is going to be 0 degrees Celsius or 273.15 Kelvin, which is the freezing temperature of water or the melting point of ice, and when we have a pressure of 1 bar, which is exactly 10 to the power 5 Pascal pressure, which is the atmospheric pressure at sea level. So this is what we are making the temperature and pressure constant as. So we have made the temperature and pressure constant, which is at 0 degrees Celsius and 1 bar pressure. At this temperature and pressure, if we measure 1 mole of a gas, how much volume it is going to occupy, it is going to be 22.7198 liters, which you can say approximately as 22.7 liters. Now another term that we learn over here is going to be SATP. Now SATP is standard ambient temperature and pressure. Okay. Now when we are seeing that STP, it is a temperature of 0 degrees Celsius, which is very difficult for us to cool every time a gas to 0 degrees Celsius and then measure the volume of the gas, right? So what we have is the room temperature, which we generally take to be 25 degrees Celsius or 298.15 Kelvin. So at this room temperature of 25 degrees Celsius and the same pressure, that is 1 bar pressure, which is exactly 10 to the power 5 Pascal. This is called as SATP, and when we again measure the volume of 1 mole of a gas, okay, so the molar volume of an ideal gas, this is going to be equal to 24.789 liters per mole. So these are something that you have all to learn, okay? So what is the temperature, what is the pressure, and what is going to be the volume of the 1 mole of gas. Fine. So these are something that you have to learn very importantly. And one thing more, while you're going to see the your books, what you will be finding is that there is a previous standard which is generally used, and it is still frequently used because all the data that we have for the experiments is all old data, right? So what we had previously was a different definition for STP, and according to that STP, the temperature was the same, that of 0 degrees Celsius, but the pressure was slightly higher, that was 1 atmosphere pressure. And 1 atmosphere pressure is not 1 bar pressure, it is 101.325 kilopascals. So here we have 10 to the power 5 pascals, here it is slightly higher, right? So here obviously the volume is going to be slightly different also, and here what we have as 1 mole of a gas or a combination of gas, it is going to occupy a volume of 22.413996 liter, which we generally take as 22.4 liter. So depending upon what type of question you have, you are already given what volume to use. You can use 22.4 liters or you can use 22.7 liters, but just remember that 1 mole of gas at STP is going to occupy a volume of 22.7 or 22.4 liters depending upon the question. And as SATP, which is going to be at 25 degrees Celsius, the volume is going to be 24.789 liters per mole. Fine, I hope this is clear. Now, when you're going to do the calculations related to the Avogadro's law, please do remember that the number of moles of a gas, this is going to be equal to M by capital M, where M is going to be the mass of the gas under investigation and capital M is going to be the molar mass. So this is something that you have already been doing from the start of your class 11th, if not earlier. Well, you have been learning about the mole concept from class 9th only. So you all know that when we are going to divide the mass of the gas by the molar mass of the gas, what you will be getting is the number of moles of the gas. So in your questions, you may not always be given the number of moles of the gas. You may have to find it from the mass of the gas. Fine. Now another thing is that we know that V equal to K4 into N, and when we replace N by small m by capital M, what we will be getting is this relation, right? So V is equal to K4 M by M. Now we can take this capital M to the other side, the molar mass on the other side, what we will be getting is that M is equal to K4 M by V, and the mass of the gas divided by the volume of the gas, this is called as the density, right? So we can replace this by d, and what we will be getting is the molecular mass of a gas is going to be equal to K4 into d. So what we can get a conclusion from this is that the density of a gas, this is going to be directly proportional to the molar mass of the gas. Okay. Now, when we have done all these four laws, you can develop an understanding that a gas which is going to follow the Boyle's law, the Charles law, and the Avogadro's law strictly, this is called as the ideal gas. Okay, but such a gas is a hypothetical gas. It is not going to practically actually exist. Why it is not going to exist? Because for an ideal gas, what we consider is that the intermolecular forces, they are not present between the molecules, right? But actually it is not going to happen in real life. There are going to be some intermolecular forces present, and the real gases, they are going to follow these laws that we have learned now only under certain specific conditions, when the forces of interaction, they are practically negligible. In other situations, these are going to deviate from the ideal behavior. So if you look at this data of some of the gases, their molar volume at STP, that is 273.15 Kelvin or 0 degrees Celsius, and 1 bar pressure, you will be seeing that argon, this has a volume of 22.37, carbon dioxide 22.54, dinitrogen, that is N2 gas 22.69, oxygen gas 22.69, hydrogen gas 22.72, whereas for the ideal gas the volume is 22.71 liters. There is a slight variation, and that is because these are all real gases. There can be slight variation because we are not having the intermolecular forces of between the molecules just to be absolutely zero. There are going to be some forces present. There is going to be some change in these laws that we will be further studying in this course. Fine. So that would be all for this lecture. The discussion is going to continue further on what are ideal gases, what are real gases. There's lots more to be covered in this course. But on the next lecture, we will be discussing the problems based on the Avogadro's law, which is going to be very helpful for you to understand this concept further. Right? So please do subscribe to the channel if you have not done till now, and also do click on the bell icon so that you get a notification the moment we put up the new lecture for you. And also, if you've liked the lecture, please do click on the like link. It really motivates us to make more such lectures for you. So see you again. Have a nice time. God bless you.